So there's a few new places for me. I started my career as an apprentice. So I started off on the shop floor and then worked my way up into growing up. So I spent most of my career doing sort of what you're doing. So working design, draftsman, design engineer, classified design engineering. And then I worked in IT for a little while before coming to ADA. The last company I worked for was Toy Mining Machinery, and they have about 60 seats together in Australia, quite a number more overseas, and they run bulk, so they have about 60 sets of bulk running in Australia. So, so for those people who are a bit scared of bulk, I can assure you it runs fine. Okay, so what I want to talk about today is basically the enhancements to Inventor, what's the Inventor Professional. This is stress analysis, and then I'll talk about the document management. So I'd like to show you some 3 areas of stress analysis. First is dynamic simulation. Now, Inventor 2009 and previous versions had simulation. So there's just been a period of enhancements there. Then I'll go into the FEA. So because the dynamic simulation has been there before, and I'll be covering FEA further on, I'll sort of skip over the FEA fairly quickly this part of the demonstration. The enhancements to dynamic simulation is basically a browser enhancement using Ribbon, and also a big feature here is the synchronization of the constraints. So previously, when you would go into simulation, all the constraints would disappear and just become joints. Now the constraints are actually shown within the joints, so it's much easier to find out what's going on with all the joints. So I'll just jump into Inventor and show what's going on with this. What I'll show is this car seat. This car seat has a little red dot, yellow dot here, which is basically a load would be where someone is sitting. And I'd like to analyse a link down here, so I'm just going to drive this so I can see what's happening with the what's happening. So I drive this up and down. So you can see that. So first of all, I'd like to just change my representation so we can see what's going on with this.
Expand your browser as well.
See everything on the screen there. So basically, we've got this motor here driving the seat up and down. And this yellow dot here is still here showing where the load is situated. So I'm going to dynamic simulation, and it's come up with this over-constrained situation. Previously, this was very hard to work out what was going on. But now we can see here the constraints have come through. Constraints been converted into joints, and we've got the icons here showing where our problems are. So I'll just change this to show the mobile groups, show what's going on much better. So now we can see that all the green parts move together, and all the cream parts here move together, so we can visualise what's going on much better. And looking at this constraint, so this point here and this one here, they're essentially the same, and it's come through from the constraints, and that's why we have this open constrained situation. So now we can expose the constraints we put on in the assembly situation, and we can suppress those. So that's got us down to a couple being open constrained. So we look at this one here and here are much the same, so let's press this one to go. Is to turn this one off. Okay, so that's probably the biggest improvement of being able to see what's going on there. So, who uses dynamic simulation? No? Okay, well, I'll just run through this and drop the simulation into FEA and show how it all flows through. So, the part I'd like to analyse is this little link here, the blue one. And so the dynamic simulation here is a little hash on this joint showing the, this is a, it's got motion attached to it. So just look at the properties of that, and you can see you have a, it's driven from going from 0 to 10 millimetres per second and then drops down the other end, so over 3.5 second time period. This can be modified and modified with the load. What goes on there is that can be done. So here we have the force, and this is like simulating somebody sitting on the seat. And we can edit this load, and this has 200 newtons, some fairly light here, but we can just show what we can do here. We don't have to have just a static load, we can actually put dynamic loads on here. So we have something like going from 200 maybe to 250 over the 3.5 seconds, and then we can add other loads on top of that. So just wipe that one out. So we just start again. Just cancel that and come back in. Probably use this way. So we're just going for the ramp moment, going from 200 to 250. And then we'll add another one on top, so I'll get a second one here, which is the, could have a sign like here, so we can add, say, 50 newtons and 1 hertz. So we can just get this dynamic loading onto our set. So somebody's bouncing up and down while gaining weight. We can see the static load at the moment. So 200. Okay, once we have that set, we can now basically run the simulation. We have a output graphic here. Let's clear this, and I hope there's enough real estate on my screen. Okay, so if I try and put the model behind. Okay, so what we can do now is run for 3.5 seconds with 35 time steps set up. So it's 0.1 second time step. And we'll see the simulation of the model back there, and the output. Now, the output here I've picked on 0.12 and 7, so this is the two ends of my link. So, first of all, I'll just show the force at this end. We'll run a simulation. So over the time period, it will give me the force. And so I can also check the moment at that point. Scan that and see we've got a moment on there, which also changes over a period of time. And at the other end of the link, we've got basically the opposite force and the opposite moment.